Recording. Yeah, we're going to be talking about the call stack, basically what it is. Again, this might be a new term to some of you guys. Others may have heard of it before or are totally familiar with it. Again, not too difficult of a concept to understand, but definitely important to know in terms of software development, kind of know what your application is doing. And we also be talking about recursion, which is just another tool to add to your toolkit when you're trying to tackle algorithms. All right, so to start, we're going to be talking about the call stack. So, quick question, anyone can answer. What is a stack? Just in normal layman's terms, how would you describe a stack? Anyone want to take a stab at it?
Stack of is it a queue? Okay.
Sorry, I guess I should be calling on people because we have people. Don, I think I heard you saying something, so go for it.
I said a stack of plates at the buffet.
That is a great example. Sorry, Zoom is a pain for me. Yep, a stack of plates. That is a great example, and actually the example I was going with. So that is a good example. To describe it, I guess, anyone want to take a stab at it? Let me call on someone. Alex Saunders, if you were to try to define what a stack is. So Don gave a great example of it, like a stack of plates. How would you just more formal definition, if you could, for what a stack is in your own words?
So I would say I'll know it as more of the queue. So you have first in and first out, and then you have also like last in, first out. And so it's a different way of essentially a queue of items.
Mm-hmm. Yep. Yeah, definitely got those key terms down. So LIFO and FIFO, we'll talk about those. Yep, that I would say is a great definition. Let's call on one more person. Jeremiah, if you were, again, just to describe stack, and we're just talking about the real world, don't think anything programming specific, what would you describe a stack as?
A group of like objects just together and accessible in one area.
Yeah, so I would agree with you on the second part. So the first part, I would say you could have a stack of various objects, right? So like, I'm trying to think of stuff I have here again, I guess. So I have, you guys can see, I have a stack, I have a clipboard, I have paper. So you can make a stack out of different objects. So I would hesitate to say they always had to be the same objects. But yeah, I think we all generally, I hope, have a good understanding of what a stack is, generally speaking. So I would define it as like a vertical pile of objects, usually one on top of another. Now, you don't always have to have like one on each layer. Like you could have, like a pile that's like a pyramid. I'd still call it a pile because it's stuff on top of other stuff. Again, a very simple generic definition. And Don actually read my mind. So the example I went with was a stack of plates, right? So let's actually just talk about a stack of plates. So when we're trying to take a plate from here, most of us will probably just take the top plate. Let's assume we have one hand to access stuff. Like if we had two hands, we'd probably lift up some plates and take a middle one. Let's just not get too complicated. So let's just say, quickly just grab a plate with one hand. Most of us are probably just going to grab the top plate because that's the access point, right? There might be a few rebels out there that might try to just grab a plate from the middle. You do you, I guess. But generally speaking, a stack, we access items from the top. And then when we're thinking about when we're building up the stack of plates, how do we build it up, right? We start with the plate at the bottom. So we place a plate at the bottom, and the next plate that we're gonna add on to the pile, we add on top of that, right? Usually we're not gonna sneak it underneath. Again, we're just going with the common case. So yeah, again, a stack, we all deal with these, in our daily lives. Like you might have a stack of papers on your desk right now. You might be eating, Pringles out of a can. That's a stack of chips, right? But yeah, so basically we build from the bottom and then we take from the top. All right, so we add stuff on top of each other and then we remove from the top and go towards the bottom. All right, so that's in the real world. A stack is just a vertical pile of objects. Now, what is a stack in the programming world? And I think Alex kind of covered this. So it's a data structure that has a few key features to it. One is that it stores objects in ordered manner. So we've talked about ordering before. Now let's kind of cover that again. So there's an idea of sorting and there's an idea of ordering. We want to make sure that you don't get those two confused. So when we talk about ordering, it just means there's a set order. Sorry, I probably shouldn't use the word in its own definition, but there's a set, I guess, scheme, I don't know if that's a better word, in the way that the items are are ordered in the data structure. So if I, if they don't have to be in order, as in they don't have to be sorted. So I can have like a large object at the bottom, and then a medium-sized object, and then a really large object on top. There doesn't have to be any rhyme or reason to the way the items are ordered. It just says that items are ordered in some particular manner, usually in insertion order. Whereas sorting is where you actually have that categorization or criteria where like you might order it from big to small, or like heaviest to lightest, whatever criteria you have. That's where sorting comes into play, where you have some rhyme or reason for your ordering, versus ordering is just some order, doesn't need to have a criteria. All right, another key feature of a stack in the programming world is that this data structure provides a single insertion point. We call that the push point, and then a retrieval point, which is the pop point from the top of the stack. So again, if we go back to the plate examples, the top would be the top plate. In the same respect, a stack has a top point where things are being pushed to and popped from. So again, we have that stack of plates and we need to add a new plate, where we're going to add it to the top, right? We need to take a plate from that stack. We're going to take it from the top. So that's, again, just a visual, I guess, representation of this data structure. All right, so we push to the top and pop from the top of the stack. And then as Alex mentioned, he nailed it, LIFO. So stacks are LIFO, which means they're last in, first out ordering. The opposite of that, so we're going to be covering data structures more tomorrow. Sophia is going to be coming in, so I don't want to take away too much from her material, but a queue is another data structure that is very similar to lists or stacks, but they are FIFO, which is first in, first out. So queues, we see these in our daily lives, like when you line up at like a customer service desk, the first person in line gets first access. If that was implemented as a stack, I think there'd be a lot more chaos in the world, a lot of angry people. If the last person in line gets first access, that'd be, not a good system. So yeah, lines that we deal with, like grocery store lines or whatever, amusement park lines, those are all FIFO because we're queuing in order. Whoever got there first gets first access to get out of that line. But we're talking about stacks today. So again, stacks kind of the opposite of queues. Stacks are last in, the last item in is the first item out of a stack. Can anyone give an example in a programming sense where stacks are used? And like on a daily basis, we definitely encounter them. So I want to know if anyone can name them off the top of their head.
Recursion.
What was that, James?
Doesn't recursion use like stacks a lot? Or it's an important concept in recursion.
Yeah, definitely. Yeah, recursion. Yeah, so we're leading our recursion discussion with the call stack because it is important to know. But I guess just again, in your daily lives, like something that you probably do every day, where do you see a stack implemented in software?
Lists.
What was that?
Lists, just list structures, creating lists, arrays.
Oh my God. Lists, I would say not quite, because again, lists give you access anywhere from that data. So if I have my coding window up somewhere, let's create a new file here. I probably don't want to do this in budget. Sorry. Yeah, let's do that here.
Yeah.
Create a new file.
Okay, there wouldn't for loops then? Wouldn't that be more?
Stack.py. Not quite.
No,
So for loops will be example of not using the stack in our application, but let's just talk about lists. So lists, if I created my list equals whatever, some random numbers, again, lists don't have to be sorted. They can have different types too. If I want to put in a string here, sure. Whatever goes. There is an ordering here. So again, I can iterate through this data structure in order. I can get the 6 first, then the 3, I can go reverse order, whatever I want. So lists give you a lot of flexibility. So I could access something from the middle. So I want to do my list and print out the third index. So index, that's a bad example. The item at index 1 will be this 3. So lists are really flexible and they give you access to any of the items that are involved. A stack, on the other hand, is not quite the same. So this is going to be a list because in Python, there's no actual stack data structure. But let me implement a list quickly. It'll be a fun little exercise, or minus the fun part. But I'm going to create a stack class.
Fun exercise minus the fun part. I like that.
So I'm going to create a stack object, and this is going to be, again, very, very, very similar to a list. So init, thank you VS Code for dropping all the stuff in here. Okay, so this is actually going to use a list, but I'm going to, again, with Python, things are harder to kind of explain the way I want it to, but hopefully you guys can play along with me. So I'm going to create, not a path, what am I doing? That's going to be push method, sorry. I'm going to push some value. And the self.data.append value. And we're going to have a pop method. Def pop self. And we'll do self.pop. So pop's a method on lists that already exists. So that kind of makes it nice. Return. Okay, this is my stack. This is the implementation of a stack. The key thing here is you are not supposed to access self.data by yourself. So if I do something like data, all right, so I created a stack class, and I could create an instance of my stack. Okay, so this is a list. A list gives me access to any point. With this class, I'm just telling you guys, because in Python, you can't restrict data access. You should not touch self.data yourself. That's why we have these methods. And as we talk about class design, usually you want your data members and your data methods to be all encompassing. So your data methods should be the one interacting on your objects. You shouldn't be doing that manually. I hate to kind of quickly jump back to our budget example, but I'm going to. Budget, where'd you go? Okay, so just to highlight the point again, if I go to my budget class, right, I have self.transactions. I could theoretically access this from my interface class, right? So if I go down to where I'm adding a transaction, it is totally possible for me to do self.budget.transactions, because that's an instance attribute, and I can just do append right here. Again, Python lets you do this. You shouldn't be doing this. For the most part, you should never be touching instance attributes directly unless you've designed it in that manner. But for the most part, you should be using methods to update this, instance attribute. The reason being, if we remember, again, sorry, I'm jumping back to our earlier challenge, add transaction does something extra, right? We added this extra check to make sure that we're not spending more than we have. So if we're just updating our data structure right away, we're basically circumventing that check. That is not good practice. We should be adhering to add transaction. And again, that's the encapsulation or abstraction part of it. In that, again, I see Jack on my screen, so I'm just going to use them as a reference. Let's say Jack created this budget class. I should trust that add transaction is going to do the correct thing. I shouldn't, again, try to update the data myself. Jack created a method that's going to update the data in an appropriate manner. I don't necessarily know what it's doing. Again, since we coded it, we know it's actually checking against our monthly income, going to raise an error, yada, yada, yada. But again, the whole point of class design is so that the data methods act on the data themselves. You shouldn't be acting on the data. So that was a kind of a long-winded tangent, but I just want to highlight that. Same thing with my stack here. I can access self.data, but I shouldn't be doing that. I should be using the methods that are provided to access the data for this class. Is everyone on board with that? Okay, so assuming everyone's on board with that, now that I have my stack, my only options are to push. So I can push new values, like let's say I want to add 7 to it, or I could do my stack.pop. I don't have control. I don't have this level of control where I could say, hey, what's the first item in my stack? Or sorry, the second item in my stack. Stacks only give you access to the very last or the very top of the stack. So in this case, if I pop, it's going to remove the 7 I added. But if I pop again, hopefully you guys are familiar with the pop method. It's going to keep trimming it from the very end.
Pop needs to be self.data.
Yes, thank you. But yeah, so that's how stacks work. They only give you one access point. That's at the very end or the very top of the stack. All of this stuff down here is that you as a developer should not have access to it when you're using a stack. All right, so that's just stacks in a nutshell. What where were we in our presentation? Yep, so LIFO ordering, last in, first out. An example that I was thinking of in our daily lives is web browser history, right? So if I go to my browser, which is over here, using a dark theme, hopefully it's not too hard to see. Let's just navigate to a few pages. I'm going to go to Google. Since I like donuts, I will rep, I did that, Do Right Donuts. Hopefully they give me some sponsorship donuts or something. So I search for Do Right Donuts. I'm going to click on their site. Takes a little bit of time. Not sure what's up. All right, we got a nice splash page. Let's go to their menu. Check that out. Okay, looks like they have sandwiches. They probably should have donuts listed here. This is my favorite donut of all time, chocolate old fashioned, delicious. All right, so I went there. Let's go to one more page. Let's go to their, let's see what news they have. All right, so I clicked on news. Now, if I go to my back button here, notice that this is a stack actually. The last page I went to is the first item on the stack. So I guess it's currently on my news, so that's at the top, but if I want to hit the back button has implemented a stack so that it's going to access the last item it added to the history, right? So if I hit back, it should take me to menu, right? And that's where I was before. And then if I hit back again, it should take me to the home page. Again, so simple implementation. We see stacks every day. We probably don't think about them, but yeah, web browser is a stack. Another simple example is I can just do that right here. I hit Command Z. It took away that data fix that I had. I'm just undoing a bunch of stuff with Command Z. And then if I want to redo it, I can add that back on. But it's basically adding items to the stack based on how I type stuff. So I add a pop if I want that data back here. But yeah, so undo, redo, that's stack implementation. The undo, you build up. And then if you want to undo, you do the most recent item by doing a Command Z. Usually you don't like go back into the middle and undo something in the middle. I think with the clipboard history, you probably do that, but simple undo and redo, that is implemented with stacks. Okay, so yep, web browser history, undo, redo. There's probably many implementations of stacks that we see with our common software interactions that we do. What is the call stack now? So we talked about what a stack is. What is the call stack? That's what we're trying to get at here. So it's an ordered collection of execution context. So it's a stack data structure, but we're storing execution context. So we'll define that a little bit better. So each line of code that's executing in your application will get added to the call stack one at a time. So they don't all get dumped on there right away. Basically, Python, if you're running a Python application, is going to go line by line, get to a line or an expression, and it's going to evaluate that and put that onto the call stack. Then the call stack will execute that line and actually process it. So one at a time, if we had an application, it would add a line to the call stack and then execute it. Once a line of code is completely executed, it gets popped off the call stack. But our call stack can grow if we're using functions. So functions can call other functions. So a function only fully completes when it executes a return statement in that function. However, one function can call another function, and that's going to add on top of the call stack. So obviously, there's a lot of wordage. Let's actually see an example. So if I go back to the curriculum page, I think my donuts are still running. I should probably stop distracting myself. Let's go with this example here. So I'm copying this from the curriculum page, just a fairly trivial example. I think I already had it here. All right, so we have three functions. We have a function called first, a function called second, and a function called third. And then we invoke our first function as part of our main execution. All right, each function is printing out some items, but notice that every function or most of these functions are calling another function, right? So let's actually see what's going to happen with the call stack, just to kind of make sure that everyone understands how the call stack is operating. So here's the code. Same code that we had before, just kind of trimmed down the strings. But we have first, second, third, and we're calling first. So the first thing that happens is this global context kind of gets thrown onto the call stack. I don't have too much detail on it. It's just something at your base level. So like if you have global variables, your global context will be providing those. All right, so first thing that happens in our application is we don't execute all the functions. We actually execute first line of code, which is all the way down here, we're invoking our first function. All right, so first parentheses, that's going to call our first function. What happens is that first gets thrown onto the call stack because we're executing that line of code. And this line of code is calling a function. So we hop into that function. So now we're inside our first function, and we're executing this line, print, and printing out of the string. So we actually throw that onto the call stack. Actually, we don't do it, sorry. The application is automatically doing this for you. So the call stack is automatically managed. It's not something that you have to manually pop and push to. But yeah, so the application pushes this line to the call stack, but the print function executes right away. It's not going to call anything else really. Its job is just to output the value you want to print out the console. So that completes. It gets popped off the call stack, and notice we had our output of push first. Okay, so that line completed. Then we're able to proceed to our next line, which is second. Second is a function call, right? So we're going to put that on the call stack and then go into that function right here. Yep. And then we're going to add another print. So it gets added to the call stack. Again, this is building up. So normally stacks go from bottom up. So we have global first. Again, we're still in our first function. Even though our code is here, this call happened from our first function. That's why first is still in our call stack, because first has not completed its job. It's still in the process of completing its execution. So first has called second. That's why second is on top of first, and we're in the second function right now. We've pushed the print statement up here, and we're gonna execute it. And so it got executed, so it got processed, it did its job, which is printing a value to console. And then now that's complete, we move to the next line. There we go, we're calling it another function. So we're calling third. Notice third gets added to the call stack. Then we're gonna go into the third function, because we're invoking this function, which is defined here. Third has 3 print statements. The first print statement gets added, then it gets processed. So when we process it, there we go, we get push third. That means we just started our third function. Now our function, the actual, logic for this function is printing out hello world. So that gets added to our call stack, that gets executed and updated or output to our console. Now that we've executed the main logic in third, it's time to pop off the third function, meaning we've completed. So we're about to hit our return. So that's why I added this print statement. So normally this, these print statements are just kind of reflecting what's going on. When we push something, that means we're in that function and it's been added to the call stack. Now we're done with the third function. So we're going to print the statement, pop third. Now we get to this return statement. So the return is the actual end of the execution for our third function. So now that we return, we're going to go back to where we're executing, which is here. And notice that third got removed from our call stack because third has fully completed. All right, and then we proceed on because third has finally completed. We print another statement that gets pushed to the call stack, removed because it executes. Then we return here. Same thing happens with second. Notice second is here, where we're about to complete that execution. So we complete it. It's removed from the call stack, and we proceed. Yeah, I think everyone's with me. And then finally, once we've completed all the lines of execution with our code, the global context gets popped off, and then we're done with our application. Your application will terminate at this point because there's nothing else to execute. All right, any questions with the call stack? Okay, so this now we're getting to our main event, which is recursion. So kind of important to understand the call stack because recursion kind of will kind of not abuse it, but uses the call stack heavily. All right, so recursion. What is recursion? So recursion is something that employs recursion. That's probably a terrible definition because this is a recursive definition. We're using the word inside of its own definition. I think I did that earlier when I was trying to describe ordering, but yeah, this isn't very useful, right? Recursion, just pointing back to recursion, it's gonna go over and over. A fun little Easter egg, if you're not aware of it, if you go to Google, let's go to Google. If you search for recursion, anyone know what happens? Search for recursion.
Ask, do you mean recursion?
But yeah, notice that Google's telling me, did you mean recursion? I didn't have a typo here, but Google's just messing with me. So if I click recursion, all right, sure, maybe I had a typo there. All right, I click that. Notice I get to the same page. I keep clicking that. Again, I get valid results, but this is kind of just like a Easter egg for Google. There's a few of them. I forget. There's some that I've used before. Yeah, you can kind of search for Google Easter eggs. But yeah, that one's kind of silly, like, you know, nerd humor. Most people will be like, what's going on here? This is a bug. No, they're just kind of messing with you. But yep, so this isn't a great definition. I think a better definition of recursion is something that references itself as part of its definition. So again, similar to what we were saying before, but we're not using the word recursion in its own definition. So basically, again, it's self-referential. Anything that's kind of self-referential is kind of implementing recursion. Okay, so hopefully that kind of makes sense on a high level. But what is recursion in the programming world? So recursion, as software developers, we describe it as a process involving breaking a bigger problem down into smaller versions of itself. All right, and we'll see this with examples. Fibonacci algorithm, actually, I kind of hate myself. This is not a good example for why you should use recursion, but this is kind of just an easy example to see some benefits of recursion. A recursive function is one that calls itself, or basically invokes itself. So it can call itself repeatedly. There's no, I guess, general limit aside from the call stack size, which we'll talk about. But the Fibonacci algorithm, let's kind of take a look at that, and then that'll kind of hopefully give us some ideas of why recursion may be useful. I'm trying to use my words really lightly, because for the most part, you shouldn't need to use recursion for most algorithms you're solving. There are a few select algorithms where recursion is a better approach, but most of the time you can avoid using recursion and your life will be easier for it. But there are two main parts of a recursive function. There's a base case and a recursive case. Recursive case is just the idea of the function calling itself for further execution. The base case is very important. So the base case is actually where you stop your recursive calls and kind of just, you're building the stack up, and then eventually you're going to hit some case where you reach your endpoint and you start building back down. So this is a special condition where the function finally returns without any further recursive function calls. If you omit a base case, or rather have the incorrect base case, you'll get something that's called a stack overflow. It's probably a term that we've heard of. It's actually a website that's used by programmers, but stack overflow is, if we go back to the call stack, I guess I probably should have talked about that a little bit more. So we had our call stack here, right? So this is an area in your computer that's allocated for each application that's running. Each application kind of has a set or defined memory space. At some point, as you're adding more and more functions, you're going to run out of memory for your application. So this call stack is not infinite. It is a finite chunk of memory that your operating system gave to your application. All right, usually it's large enough where you're not going to need to run into the upper limits of your call stack. But if you have like an infinite loop, or rather infinite recursion, you will hit that, because it's not going to let you build up this call stack for and forever. If it did, you would have like severe system issues, as in your computer would crash, not just the application. So as a safety mechanism, your OS, again, allocates set memory size, and then if you exceed it, it'll usually just give you an error, and maybe your application will crash, but your system shouldn't crash in that. All right, so this, again, the call stack is just the memory space that's allocated for your application that has a finite amount of memory. So, sorry, I don't want to go through all this again, but so without a base case, you're going to keep calling that function over and over. So your stack is going to build up and up and up and up until it reaches a breaking point where your application's like ran out of memory, and then bad stuff will happen for your application. Hopefully not for your operating system. So yeah, base cases are vital for having a proper recursive algorithm. All right, so we're going to be talking about recursion versus iteration, and we'll see an example. So we'll get there shortly. What is iteration? So iteration is something we're more familiar with. We've done this a ton. It's the process of doing something repetitive. So let's say we want to count down from 10 to 1. We just go through a list that has all those numbers in it and print out each one by one in a repeating fashion. So for loops, while loops, whenever you're using these, you're using iteration. Couple notes here. all iterative solutions can be converted to a recursive solution. And likewise, all recursive solutions can be converted to an iterative solution. So again, knowing this, basically what I've said before, most of the time you want to focus on iterative solutions because it's just, they execute in a faster time complexity, and usually recursion can add some more complexity when you're not looking for it. Now, this is not always the case, but from my experience, iterative solutions are the way to go like 90% of the time. Recursion does have a unique place in algorithms, but usually iteration can achieve what you're looking for, and probably the way to go. Questions?
What about runtime?
Runtime, again, it all comes down to what particular algorithm you're trying to solve. Again, I am not an expert on this, so based on what I've read online, most of the time recursion will add to your time complexity. Again, most of the time. Sometimes though, depending on the very particular nature of the algorithm you're trying to solve, recursion actually can reduce time complexity. So it's just a case-by-case basis. It's not a blanket statement that recursion is always worse or better. It's specifically, you have a specific problem, you need to decide as a developer what's the appropriate way or the most sensible way to solve this. And that's where recursion may be the answer to that question. All right, so let's look at Fibonacci. Again, Fibonacci is not the best example for highlighting why to use recursion, but it does offer some benefits. So here's just a simple solution for Fibonacci using iteration solution. All right, so this is some of you guys did week 1, I believe. Some of you guys, I think, did it recursively, but again, iteratively, totally manageable. You create 3 variables, initialize them to 0, 0, and 1 respectively, so F, A, and B. Then you loop through your range. So if I'm trying to find the Fibonacci value of 5, for example, I'm going to loop through n equals 0, 1, 2. So I'm going to go through it 4 times. So again, a little complicated to understand what's going on here. Basically, Fibonacci, if you guys remember, basically the Fibonacci of n is equal to the 2 values before it. So if I'm looking for a Fibonacci value of 4, well, Fibonacci 4 equals Fibonacci 3 plus Fibonacci 2, and kind of see the recursive nature there. But in this case, that's what we're computing. So we sum up A and B, and then we store that in F. Then A takes the place of B, and then B takes the place of F. And we loop through this. Honestly speaking, if I were looking at this and really didn't know anything about Fibonacci, I'd be kind of confused. I'd be like, okay, not quite sure what Fibonacci is trying to compute. I see a loop. I see a bunch of values being summed and kind of swapped. Like honestly speaking, I would be kind of confused looking at this. Probably adding some comments would be helpful, but again, not too many lines of code. Like, it's pretty simple, but still not intuitive from my perspective. You guys might disagree, but honestly speaking, I'm kind of confused by this. So let's go to a recursive solution. All right, so Fibonacci still outputs the same value. We should definitely verify this, but we have recursive here. So recursive, much shorter, and I would argue is much easier to understand. All right, so I'm going to go to my coding window because I have this coded up. We have 2 implementations here. We have iterative, which we have here, and then we recursive. Recursion and iteration. Okay, both should output the same values. So let's actually verify that. I'm going to run this quickly. Let's do Python fib.ui. All right, so we get 55 for both, and I believe that is correct for fib of 10. But again, looking at these 2 solutions, a couple of things, again, stand out to me. Fibonacci solution, shorter. Again, not that my original was that much longer, but this, again, very simple lines of code. And by the nature of Fibonacci, me, as like, let's say this is the first time I've ever heard of Fibonacci, I would much prefer to see this definition, just because it tells me, okay, Fibonacci of n is the 2 values before it, and we got to repeat that over and over because we're calling the function itself. So again, highlighting recursion versus iteration. Iteration, you go through a loop and you do something repeatedly. Recursion, similar, you're doing something in a repeated fashion, but instead of using loops, you're using the call stack and basically calling the function from within the function. All right, to highlight some parts of our recursive function, this is our base case. So when n gets down to less than 2, we're just going to return n because again, if you remember, I think it's 1, 1, 2, 3, 5, 8, so forth. That's the Fibonacci sequence. The first two numbers are special case because there's no two values that precede it. So this value, there's no two values here to compute this. So for Fibonacci, the first two values, when n equals 0 and n equals 1, they're defined as 1. So that's why our base case exists here. Otherwise, all the remaining values or future values can be computed by looking at the prior two values. So this 2 is computed by summing up the previous two values. That's, n equals 0 and n equals 1. All right, so that's our base case. That's what terminates our loop, and then our recursive case is the common case where we're going to try to compute the value by referencing the past two values here. Okay, so those are a couple benefits that you might get out of recursion. Is that you get simpler code sometimes, not all the time. Depends on your algorithm. But in this case, I would say this is simpler code and more intuitive to understand. So yeah, let's talk about some possible advantages of recursion. So as we talked about, generally reduced code. So usually recursion will save you code because you're reusing, like you're taking a larger problem and just kind of reapplying it, the same algorithm for a smaller subspace. So you're kind of get better reuse of code. So you're gonna get reduced code that way. Key thing is you may get a more intuitive solution. That's not always the case. Sometimes recursion will be much more complex, just reading it. You can still solve it using recursion, but again, it's not gonna guarantee that you're gonna get a more intuitive solution. As we talked about earlier, it may reduce your time complexity of your algorithm, but that's on a case-by-case basis. Usually speaking, recursion will add time complexity, but that's not always true. Times where recursion, like again, when you have that switch in your head, if you're dealing with problems that have branching, divide and conquer, or backtracking, these are popular algorithms where recursion is probably the way to go. So when we talk about branching, we haven't talked about tree structures. That's another data structure, but we kind of just think about, let's just think about it in a normal everyday case. Let's say we're driving down a freeway and then there's a fork in the road, right? You want to take, let's say, I-80 or I-90. Which one do you take? Well, let's say you have no idea where either of them go. Well, in that case, your algorithm would basically take both paths. So your recursive solution would be like, all right, what if I take I-90? What are my options going to be there? And then if I take I-80, what are my options going to be there? Obviously, as a human, we can't just like take both paths, but our algorithm can kind of explore both opportunities. So in that case, like when we take I-90 is going to have more forks on it. Like they might have 290. I don't know all the freeway connections in Chicago, but there might be I-55 that branches off I-90. So again, when you get to I-90, you're going to have more options. So those branches, you might have 2 branches, you might have 7 branches that you encounter. These are good reasons to use recursion because it's the same problem over and over. Basically, you get to a fork, then you want to take all forks from that point, whether it be 2 paths or 7 or 20. Your algorithm shouldn't care. It should be like, all right, I have forks, let me pursue all of them, and then each of those forks may lead to more forks, and just keep going down and down that chain. That's where recursion is much more elegant than using iteration. You can do that with iteration, but your code's going to get kind of confusing and hard to manage. The reason recursion is beneficial is because you have that call stack from your application kind of baked in. So that call stack manages the context for you. And I know I'm saying a lot of words, so hopefully we'll see an example. But basically, each function call has its own execution context. So all the values are kind of stored in there. You as a developer don't have to manually store the values yourself. Okay, example. So one example, searching a maze. Again, kind of like, forking in a road. If we go back a couple days, let's jump in our calendar. Open a new one. Oscar, let's go to week 2. And we'll go to this one. Oop. Sorry, I'm trying to find Boggle. All right, Boggle. So we talked about Boggle part 2. Again, one of my favorite challenges that we give. So definitely gonna go back to it. Boggle. All right. So part 2, I think we talked about this on a high level, and I'm gonna go back to it. So this is where recursion was really beneficial. And you might, maybe kind of unfair for us to give you just challenge before talking about recursion. Again, you can solve it with loops, but recursion is the way I've solved it. So again, just think about it on just a general level. If I was trying to find a word in here, let's say I was trying to find the word ran, right? So I'm going to search for ran in this entire space. The way of iterative, or both recursively and iteration, I guess I'd use both. You just see go through this entire I guess data structure, whether it be a list or whatever. Look for an R. Somebody's going to scan through it. This would be iteration. I'm going to find as many R's as I can. In this case, there's only one R that exists. So I'll go from there. Next up, I want to search the items around it. So this is where recursion would come into play. So my search space initially was my entire grid, and I was looking for an R. Now my search space is these 8 cells. I'm looking for an A. It's the same algorithm, right? I'm still looking for something in a search space. It's a little different because my space is a little different, but the function itself is doing only one thing. It's looking for a value. Again, it might find one value. In this case, there's only one A, but let's say there's an A down here also. In that case, it's going to find 2 A's and call this function, my recursive function, twice, because it found an A here and it found an A here. It's going to do the same thing. It's going to take this A, find all of its neighbors, and look for an N, because we're looking for the word ran. In this case, let's say the A was here. It's going to find all of its neighbors and also do the same thing. It's going to look for an N. So it's the same process over and over. We're just, we're taking the string ran, we're finding the R, and then doing the same thing for AN. So our problem now is, can you find AN in our board with a few, few extra conditions? But the same thing, once you find A, our A has been chopped off. Now we're going to look for N. If this word was 20 letters long, we'd do the same thing. I guess 20 would not actually be legit on a 16 4x4 board, but hopefully you guys kind of get the idea. So again, if you want to go back to Boggle 2, recursion will make your life much more easier if you're trying to solve the part 2 challenge there. Because it's the same thing over and over, just some different values you're passing in. Okay, so searching a maze or searching a space where you have multiple options, recursion is a popular choice because it's easy to implement. The thing I want to highlight is that it's not always the most efficient solution. So with searching a maze, the reason it's not efficient is because it's going to do something called depth first search. Again, that's kind of a mouthful to say, but depth first search means it's going to take, like if we're back to our freeway example, effectively it's going to take I-90, take I-92, or I-290, is going to take every branch and get to the end of that road. And once it gets to a dead end, then you're going to say, okay, this was not the location I was trying to get to. So let's say I was trying to find my way home and I don't know how to get home. It's going to take all those paths, get to a dead end and say, all right, this was not where my home is. Then I'm going to go all the way back and then go down another path until it gets to the very end. That's called depth first search. You're going all the way, or like the entire depth before making a decision. That's usually not efficient. The better way to do it, if you can, again, as humans, we're kind of limited by physics, but the way to search is basically you search each step. It's called breadth first search, where you go each path and you take one step in each path. So I would take I-90 and drive a mile, and take I-80 and also drive a mile in my algorithm. So I'm progressing on both paths equally. And basically I'm searching each level. So again, that's called breadth first search. And that's a more efficient algorithm because let's say hypothetically, I take I-80 and the first exit I take, that's where my home is. Then I-90 doesn't have to take like, another 700 miles or whatever I-90 goes and search each of those branches. Because breadth first is gonna, if your answer is close to the top, it's gonna find that first. Is this kind of making sense? I feel like visuals would be better. I don't know if I could find a quick visual online. Visual of depth first versus. Sorry, I should probably queue this up, but gotta be some videos on it. Ooh, there's a graph. So let's see if this shows anything.
What's up, guys? Welcome back to O'Neill Code.
All right, so this is using a stack. So whenever you're using a stack, you're using depth first. So I guess I don't know quite what they're trying to achieve here, but I think they're searching for a number. So breadth first uses a queue. So the first item in a queue, so again, kind of getting ahead in our data structure talk, First thing in a queue will get executed first versus a stack, the last thing that got added. So in this case, the 1 gets added, goes to 2. I guess I'm not even sure what this is doing. So let's abandon that. Basically, depth first, not most efficient, but can get the job done. So using recursion, using a stack, and that stack gives you, I guess, a better algorithm just from understanding it, but not necessarily the most efficient algorithm. All right, disadvantages of using recursion. Requires more memory. So this is something we didn't talk about for call stacks, but every function call you make adds memory usage to your application because each function has its own execution context, which means it's keeping track of each local variable for each call inside that context. And building the stack up also. So that stack takes up memory. So generally speaking, your recursive solution is going to be more memory intensive than iterative solutions. There's generally no way to like make recursion less memory intensive. There's a way to make it kind of the same if you kind of store your intermediate values, if you can reuse them. You can kind of achieve an equal solution memory-wise, but for the most part, recursion uses more memory. So definitely losing efficiency there. But again, it comes down to what you're trying to solve. Sometimes your use case may be use as much memory as you want, just have the most elegant solution. Well, that's when you're going to want to use recursion. However, if memory is like a limiting factor, like let's say you have very little memory to work with, then you probably are not going to want to use recursion. As we talked about, in most cases, recursion is going to add to your time complexity. So again, not going to give you the most efficient solutions, but we'll give you the probably the most elegant solutions. And there are trade-offs. Again, you might think you always want the most, the fastest solution. But that's not true. Depends on what your requirements are, what your clients need. I could argue that sometimes having simpler code is better because it's easier. It's going to have fewer bugs, and it's going to kind of just be easier for anyone to understand. So the fewer lines of codes that you have, just by nature, the fewer bugs you could possibly have. So a 10,000 line application has a lot higher likelihood of having bugs than a 10-line application. Hopefully you guys would all agree with that. Again, I'm not saying all the time, like if those 10 lines are written really poorly or just really convoluted, like there are probably bugs that can creep in. But generally speaking, fewer lines of code, less chance of screwing those lines of codes up. Stack Overflow, something we talked about. So this can be a bad or good thing, kind of on how you view it. So if you have implemented recursion, but you did not properly implement your base case, which means your recursion doesn't terminate, you're going to, your stack's going to keep building up and up and up until you get a stack overflow. That's the point at which your OS says, all right, application, you're out of memory. We're just going to kill you. So basically your application will crash. Again, that could be a good thing. So I guess the mirror of that with iteration is where you get an infinite loop. So if you just run a while loop with a true condition, that loop is going to keep running basically for infinity. It's not using up any extra memory resources. So your OS is not going to say, hey, you got an infinite loop, let me stop that for you. It's just going to run forever. So we could obviously easily demonstrate that. Let's create a while loop that says true, true, and pass. All right, so this is an infinite loop. So if I run this, that's not what I'll run. I'll run fib. All right, notice my cursor is stuck here. I've not gotten my prompt back because this loop is going to run forever. We could take an hour off. This is still going to be running. All right, so again, that can be a good or bad thing in how you look at it. Sometimes it might be beneficial for you for the application to actually crash rather than hang indefinitely. So iteration, while loops or infinite loops will hang forever. Versus if I write something that's going to, let's create a recursive case that doesn't have a proper base case. So that's simple enough also. I'm just going to create a function. Let's call it forever. And forever is going to return forever. Let me invoke this function. Okay. I guess it knows that this is never going to execute. All right, so now I have a recursive function called forever. And lo and behold, all it's going to do is return forever. So it's going to call forever again. So we're going to get back in this function. And that new function call is going to, again, call forever again. You guys kind of hopefully get that. In this case, forever is going to run forever, but not really, because if I give this a go, let's actually print something so we actually see something. Print I. All right, so I guess this is going to just be printing a value and then printing the next value in that sequence. So let's give this a run and see what happens. Okay, that ran really quickly, but so it printed out several hundred instances of this. So this function was building up this call stack. So my each forever function called another function of forever. So that's what these printouts are for. But at some point, my application ran out of call stack space. So in this case, Python said maximum recursion depth exceeded, calling a Python object. So this might be a special case in Python, but I got a recursion error that was raised. So my application terminated because this was not going to end. Python's like, all right, it seems like a runaway case. So my application terminated. Both cases, infinite loop or infinite recursion, neither are good. You get different results with recursion or iteration. So just kind of understand what differences you might get. So again, disadvantage, usually you don't want your application to crash. I guess in this case, you have the ability to handle it. So maybe that isn't a disadvantage. I should probably list that as a in-between, right? Because if we go back to other tools in our tool belts, what if we did something like try running forever, and then let's have an except case. Let's actually catch that error. So I'm going to do recursion error. So specifically, if the recursion error is raised, if some other error is raised, this except statement will not catch it. In this case, let's print something out that's useful. Let's say, hey man, you probably forgot your base case. Okay, so again, this could be a benefit of using recursion in that you have the chance to catch, at least in Python, you have the chance to catch runaway recursion call. So if I run this, notice I got a friendly error. My application didn't quite crash. We gracefully handled it. So running into a Stack Overflow could be a benefit for recursion in that you have the chance to handle it versus an infinite loop. It's just stuck forever until you terminate the application kind of forcefully. Okay, so that was our talk about recursion. Let's actually see an example before we wrap up. Where are we? 7th? All right. So I'm going to take an example that we have here. Let's look at this liftoff. So we have two ways about doing this liftoff. Menu file, call it liftoff. All right. So we have an iterative solution and a recursive solution. That is my bad. These should be print statements. I was editing this too late. All right. So small typo there. Make sure you use prints with Python, not console logs. But both these are doing essentially the same things. We're taking a number, we're going to count down, and then once the countdown is completed, we're going to lift off. Same thing with recursion. We're going to take in a number, we're going to print out that number, and then recall that function with the next value in line. All right, so let's actually run these. So let's do space countdown iterative, and space recursive. All right, then do Python liftoff. All right, so we got two outputs. Notice they're identical. So again, this just highlights the fact anything you can do iteratively, you can do recursively, and vice versa. Okay, well, let's actually look at this more in detail because it's not that exciting to just see these statements. Let's actually see what's going on with recursion. So I'm actually going to copy this code and make use of a pretty nifty tool. So if we scroll down on the curriculum page, if you're following along, there's this Python tutor, which does a great job. If you've never used it before, it kind of breaks down each lines of code that you're executing and gives you a little more detail and this visual representation. I'm actually going to click on Python tutor. And let's actually run our code and see some visuals here. So we're using Python, sure, 2.6. Paste our code, and then I'm going to run, let's go with visual execution. Okay, so now it has our code, has my code that we had on the left side, and then it's going to show us some output on the right side. So actually run this line by line, kind of how we did earlier with the example in our slides. So we have space X recursive. I realize I made a mistake. I actually need to invoke this function. Okay, so now I'm actually calling. So the first thing it's going to do, Python's going to read this file top down. Even though my actual line of like execution point is 12, it's going to read this and see that I defined a function. So if I go next, notice it has this global frame. If you recall, that's what we had in our call stack, that global context. It's going to say, okay, I know that there's a function called space X countdown recursive. It's going to just, acknowledge that and add that to our global context. Next, we went to line 12, and I think it kind of jumps. Go live program. Okay. Let's try it this way. So I go to next. So it adds this there. I'm going to go to next. It's going to actually go into this function. So notice it calls space X countdown recursive. My num value is 10, because that's what we passed on line 12. We passed 10. So we're going to go into our function. I'm going to hit next. It's going to look at the value of num. That's why it's highlighted here. It's going to compare it to 0. And that's going to be false. So I kind of wish I showed it here, but that comparison was false because num was 10 and I was comparing against 0. So next we're going to print num. Simple enough. We get 10 in our output. And then we're going to call recursively, we're going to call space X countdown recursive with num minus 1. So currently num is 10. We're going to basically subtract 1 and call this function again. So if we call it again, our call stack is kind of building downwards. Normally you see it building upwards, but it's the same principle. So now we have another call to space X countdown recursive, but notice our num value is 9. The key thing to remember here is that this function call before it still has its own value of 10. It's not using the same num value. These are two separate function calls with two unique values of num. So this is, again, the execution context I was talking about with the call stack. This function has its own execution context. It is not it's not sharing anything with this call to SpaceX countdown recursive. Okay, so we're going to proceed. We'll do the same thing. We call recursive again. Notice num is 8. We could do the same thing over and over. It's going to build up. Maybe this is a longer example, but we get all the way down to 2. Then we get down to 1. All right, so we get to 0. Once we get to 0, we're at this base case. So when we get there, notice we hit a return statement. We're no longer returning a function call. We're actually just returning a value. So if we look at that down here, hit next. Notice we had a return value. Currently it's none, but I guess that's returning none. Yeah, so print statement returns none, but now that we had a base case, we're going to start working upwards. So this return call from n equals, when num equals 1, that's going to return because this is returning from this return call. Does that make sense? We've built our stack all the way up, and now we finally reached our base case, which is returned actual value. In this case, it's none. So this return none, so it's going to go back to the previous function that called it, in this case, which was SpaceX countdown, and it's going to return there. And so now this return has something to return from that previous function. Sorry, that's a mouthful to say. Basically, now we're just we're working our stack down because we're popping off the top because each one of those functions is actually returning a value. It's not making a further call into SpaceX countdown recursive. So we're just building up, and our output has already been put up there. And then finally, once we get to the end of it, we completed this call because all these recursive calls were stemmed from line 12. And then, we get our output, which is what we expected. Okay, so the key thing I wanted to show here is that each function call has its own particular values. However, I guess I should amend that with this is only true for primitive data types. If I had a list in here, it's gonna be a little different. So let's actually add a list. So let's say my list. Lists aren't copied by default. So if I add some list here, 1, 2, 3, each list I'm passing is shared because just the nature of primitive and non-primitive data types, lists are not primitive, so they don't get copied automatically. If I did want to copy it, I would have to manually copy it. So one way to do it is using slice syntax. Again, a lot of stuff we went over before, but this will actually create a new copy so that, you know, let's say I was appending my list that append from. So in this case, if I didn't copy, I'd be using the same exact list. So let's just create an empty list. It's going to append to it, and then I want to print out my list at the very end. So I probably should do my list equals an empty list, pass that here, and then print it out. All right, so if I ran this, I would expect that my list should be appended with 10, and then 9, and so forth. Okay, because I'm passing the same list around to every function. They don't make a copy of non-primitive types, so if I ran this, what do I want to do here? And 0, print my list. All right. So first, all right, so if I ran through this, notice that my list is pointing to the same thing. This is, again, very helpful, I think, Python tutor, so that visually shows you what items are being pointed to. So notice that my list is always pointing to this list that exists out here in the global context. Whereas num is created new each time for each function call, but my list is pointing to the same and exact list that I created initially. So I get an output of 10, 9, 8, 7, 6, 5, 4, 3, whatever. If I copy my list, though, that would be another thing. So let's copy it inside my function. All right, so now I'm creating a brand new copy. That's not going to achieve what I was achieving before. Basically, I'm passing it my list. My list gets here. I append to my actual list, but then every future recursive call creates a new list. So my original list is going to be unmodified after the first call. So if I analyze that correctly, I would expect my list to only have 10 appended to it. All of these are going to be brand new lists that we append to, but never use otherwise. So if we run that, let's go back to first. All right, so we create my list. It's an empty list. Then we make a call to SpaceX counts down recursive. We append right here. Right, so we append. Notice that 10 got appended to my list. But now when we go to the next call for num equals 9, notice we created a brand new list. So our original list is kind of just sitting out there, but we're no longer touching it. We're going to be modifying it. So now each time we make a function call, it's creating a new list, a new copy. So we are still building this up, but eventually we're just going to get rid of all these lists. So we keep running this. We're making a lot of copies. So again, we're using a lot of memory here. All right, so we get to our base case down here at 0. Now when this function returns, this list is no longer referenced, so it's going to disappear. Notice it just went away because there's nothing referencing it. So it basically built up that list for nothing. And now all these lists are going to just die out. And then our original list is still pointed to by our global context. So we still have that particular list. So I would expect a 10 to be output here. Any thoughts, any questions, concerns? I know that's
So from what I'm understanding, for the most part, other than visually, it seems like the recursive case is kind of worse. Is there any off the top of your head example where a recursive answer would be better, like functionally or memory-wise or anything like that?
Good question. I don't have anything off the top of my head, but let's see if we come up with something.
Or any situation in which like recursion would be better to use like functionally. Yeah.
So I am going to say there are use cases where recursion will be better time efficiency wise. I don't have one off the top of my head, so I apologize there. There's this pretty common problem called the Tower of Hanoi that you can solve using recursion. It's going to be easier to solve it with recursion than iteration, but I'm actually not sure if they're faster. So I don't know how to process this. Probably not what I'm looking for. All right, time complexity of Tower of Hanoi. So space complexity is O of n, exponential. We're going to be talking about time complexity later this week, so if you're kind of confused by that. Yeah, to answer your question, Andrew, no, I don't have anything off the top of my head. But yes, there definitely are cases where recursion will be better. But with that said, as I noted, from my experience, probably 95% of the time, just stick with iteration. Don't especially for your coding interviews, like when companies give you coding challenges, don't try to just use recursion to try to wow them. Be like, oh, I'm going to use recursion so they'll think I'm awesome. Go with what makes sense to you, and as always, try to get to a working solution. So recursion can be, again, mentally kind of tough to visualize. Sometimes it's easier, kind of just depends on the problem, but just try to solve the problem that's given to you. So iteration for me is simpler to implement most of the time. But again, for some cases, recursion might be the answer. Again, just highlight those, anything that involves branching or divide and conquer. So divide and conquer, it's the idea of like, let's say I'm trying to, find a criminal from a group of 100 people. Well, then I'll break them in half basically and have maybe I'll interview 50 of them and I'll have Andrew interview other 50 of them to kind of get their stories. Or we break down further as in Andrew can outsource and probably give Don 25 of those people to interview, and I could also, so basically same thing, we're doing the same thing. We're questioning these criminals. We're breaking it down into smaller chunks so that, I don't have to go through all 100 of them myself. Basically, me giving it to Andrew is essentially calling a function with half the group. So I'm saying, hey, function of questioning criminals, take this half. I'm going to call another function and take another half, and it's going to work its way down. The benefit of that is that, let's say Andrew finds the criminal in someone he's interviewing, I don't have to continue my work. That kind of saves time because both of them can kind of execute together. Again, this is if you're doing breadth first search, but yeah, anyway, divide and conquer it's pretty common where you can break up larger problems into smaller units. Recursion can be useful there. Backtracking is usually with searching a maze. Usually you're going to go down a path and then you might find the wrong one, and you might go back to a common point where you have another fork. I guess that's kind of like branching. But yeah, so recursion can be useful. My experience, usually you're not going to deal with it too much unless the algorithm is meant for recursion. Key takeaways, pretty high level here. Just kind of understand the stack data structure. Again, tomorrow, Sophia is going to be giving a presentation on data structure. So I'm sure she's going to talk about stacks, queues, probably talk about linked lists, trees, graphs. There's a whole list of data structures out there. It's a lot of theory again. For our purposes in our curriculum, lists and dictionaries or hashes are basically all that we use. We don't really use sets too often. We talk about sets. Linked lists and stacks and queues. Usually you won't use them, but they can be beneficial, so they're good to know about. Know what a call stack is and how it's used by your application. Again, we talked about that. Each function call kind of adds to the call stack. Each line of code gets added to the call stack and executed. If it completes, it gets removed from the call stack from the very top. And the recursion, again, kind of understand what recursion is, how to use it, when to use it. Again, how to use it is basically a function that calls itself. That function should have a base case and a recursive case. So the base case is really important. It should have a terminating point, otherwise you can get a stack overflow. When to use it, that's a little more ill-defined. Sometimes you read a problem and it kind of just smells of recursion. It's kind of that experience of like, okay, this seems like I could break down into smaller chunks. Let me just try it recursively, because it might be easier to implement recursively than iteratively. Again, we're not talking about complexity. Again, iterative solutions usually are more memory and time efficient than recursive solutions. Okay, that was a lot of talking. I want to make sure we leave off on a good point. So what questions do you guys have about stack data structure, call stacks, or recursion? Okay, I assume you guys might have more questions tomorrow when you get to tackle some challenges tonight. Let's actually talk about the challenges for tonight. So where are we? We're on June 7th. We have 3 challenges for you, kind of following the pattern of last week. Each night we're going to have a general OOP challenge to make sure you guys don't forget about OOP. because it's a very important concept to kind of know and make sure you understand thoroughly. We do have a recursion challenge. Let's open all these challenges up. So our app users 1, this is going to be a 3-part series. It's kind of a high level, kind of similar to budget. We're just asking you to, we give you a high level information. We're asking you to just implement a basic class given the requirements. So this is more introductory, just again, kind of brush up on your OOP skills. Here, we're just asking you to create a user class that has various instance attributes, and we're just asking you to create a few users. Very basic. Again, maybe kind of a step back in terms of what you're doing with like budget and some of the other OOP challenges, but kind of just make sure you guys don't forget about classes. Recursion challenge. So we talked about divide and conquer. So there's a good, probably a better explanation than what I provided. Wikipedia, obviously, a good resource to read about it. But we're going to ask you to kind of go back to some past challenges and see if you can implement them recursively. Now, I know some of you guys already may have done this, so maybe you already got ahead of the game. We did Fibonacci recursively, but let's see if we could do factorial recursively, palindrome, 99 bottles, and Roman numerals. So again, some of you guys might have already done this. It's kind of good to get the experience of just seeing how to convert an iterative solution into a recursive solution, just to kind of understand the particularities of using recursion. Otherwise, hopefully this shouldn't be too much of a stress because your algorithm essentially should be the same. It's going to be structured a little differently, going from iteration to recursion. The fun one, I think, is binary search. This is a very common search algorithm. Kind of just makes sense. Again, Andrew's on my screen, so I was going to pick on him. But if I ask Andrew, hey, Andrew, guess a number between 1 and 100.
73.
73. So then, he picks 73, and then I'll say lower, and then he'll pick some number in between there. Let's kind of change the requirements. Andrew, let's make this optimal. So what's the least number of guesses you'll need to take? So let's say find the number I'm thinking of in the least number of guesses. If I asked you to guess a number between 1 and 100, how would you attack that?
50.
Yep, you go in the middle. The reason you want to go in the middle is because you want equal halves. When he went initially with 73, again, he was just trying to randomly guess. If he guesses 73, the problem with that is that if it's lower, his search space is going to be 72 numbers. So it's going to be still potentially more steps than he optimally could have needed. So yeah, he went with 50. If I say lower, then what would you pick next?
25.
Yep, kind of get the idea here. We've all played this game before probably, where we're trying to just narrow down choices. Again, the fun way to do it is just kind of randomly guess. But the optimal way to do it is kind of just divide into equal segments so that you can have the fewest number of searches. So that's what binary search is going to effectively do, is you take any initial input and just keep slicing it in halves until you find where you're looking for. So as Andrew was doing, like he has 50, so now he's got a dividing point. Either it's between 51 and 100 or 0 and 49. Hypothetically, it could have been 50. If it was, he got it on the nose, so he would find it right away. But that's what binary search, again, you'll see this often in computer science or just software development. So kind of try to implement this on your own. I would say don't Google it because, again, it's a popular algorithm. You could find the algorithm for it easily. Try to figure out if you can implement this by following the steps here. So again, we're not checking you guys, we're not mandating anything, but I would say try not searching for the solution without trying to implement it yourself. Fun little challenge, and definitely recursion is kind of nice to use here. Okay, so 3 challenges. Binary search, from what I remember, some students definitely found that challenging. So don't be surprised or don't feel bad if you're kind of stuck and trying to say, hey, I know what I want to do. Like conceptually, it's really easy to understand what binary search should be doing. Implementing it is another beast in itself. So simple algorithm, but complicated to implement, let's say. Okay, that covers the morning lecture. I know we're hitting noon. Before we break for lunch, last thing I want to go over is the calendar. I think someone did ask how to access this. I'll try to paste the link. There should be a way to share it. But just looking at the calendar for this week, as mentioned, as advertised, Sophia Beal is going to be coming in tomorrow at 10 a.m. She is a developer at Apple, I believe. Very talented. She loves speaking about code. So she's going to be talking about other data structures. Some of them I kind of name dropped, like we talked about stacks, queues, trees, graphs. What else? We have sets, we had hashes. Again, so many data structures out there. Hopefully she'll give a good overview of a lot of them. Linked lists, another popular one. She's going to also be doing a roundtable during lunch. So please make your lunch plans appropriately. So she's going to be going until 1 p.m. So if you do have lunch commitments, either try to reschedule them or, just, please stick around for the roundtable. It's highly recommended. We're not going to say it's optional. It's definitely not optional. It's something you should be there for. So tomorrow, different schedule over lunch. We also have Nicole Carpenter coming in 2 p.m. on Thursday. So a couple guest lecturers, always love to have guest lecturers. And then also a Beyond Tech, diversity and inclusion. I believe we have a student, Emma. She was a former student at Platoon. She's given this lecture before. Great material. So a lot of good speakers coming this week.
Also, I don't know, Anka, we're going to go over the career prep or the career. So usually today, I know if you went to the week view, James was supposed to come in today. However, he couldn't make it today, so he's coming in tomorrow at 5:30.
My apologies, I wasn't showing the evening, but yeah, definitely stuff going on in the evening. So we have our TAs coming in, as Tom mentioned, career coaching part 1. James is kind of a pleasure to listen to. He's really charismatic. He's just kind of enjoyable to hear out. So I always enjoy his presentations. So yeah, definitely make sure you stick around for those. Again, career coaching is just something that is definitely going to be more meaningful as we get towards the end of the program. You guys are going to be interviewing more. So I find these really beneficial. So if you're not going to attend it, I was going to say it's definitely at your loss, but up to you guys there. Otherwise, yeah, TAs will be there Monday through Thursday as normal. Last note I want to add is assessment 2 is this Friday. So please be prepared for that. I know that on Friday we didn't get a proper OOP review just because we had a lot of things going on that morning. So we'll try to make time for this week to make sure we have proper OOP review. Might be Friday or might be one of these days during the week. But this assessment will be heavily OOP design related. So, the first assessment was algorithm space. This one's going to be designing and using OOP. So along lines of the budget challenge, again, definitely not an easy challenge, especially conceptually designing everything out yourself. But assessment 2 is going to be similar to that, not quite that level, perhaps. Any questions about the schedule for this week? Okay, with that, let's drop off for lunch. Today's Monday, so not a mandated pair programming day. Work on the challenges, definitely catch up on challenges from last week if you finished today's challenges, but make sure you're keeping pace. Again, we're not heavily, checking you guys and making sure you guys are submitting them, but if you guys aren't submitting them, then you're not going to be prepared for our assessments, and we want to make sure you're understanding the material, and the best way to know if you actually get it or not is by doing the challenges, right? So with that said, go ahead, enjoy lunch. Please be back around 1 o'clock to do your challenges. And as always, TAs and Tom and I will be available for answering any questions that you guys might have. Regarding assessment 1, Tom and I are grading those, so we'll have those likely by tomorrow. So if there's anything specific you guys want to go over, we could definitely talk about that maybe tomorrow afternoon or Wednesday afternoon with regard to grades.
Awesome.
All right, guys.
Thanks, Anka.
Have a good lunch. See you guys.